Hello, everyone. Welcome to Math 341 Linear Algebra. I'm sure your instructor has explained to you the purpose of these videos. I want to emphasize what the purpose of the videos is not, and that is they're not a replacement for the textbook. They're to replace lectures in the traditional sense. But yeah, there's of course details in the textbook that don't get mentioned in lecture. They're still worth reading over, especially if you're struggling. I'll follow the textbook pretty carefully, so that it'll be easy to see where to go in the textbook if you get stuck on something. All right, let's jump right into it. We are in section 1.1, systems of linear equations. So recall we're given a system of two equations and two unknowns, like say x minus y is equal to 3, 2x plus 3y is equal to 1. Then we can use algebra to find values for x and y that make both of these equations true. And the basic fact that we use, the basic algebraic fact that we're using here is that if you have an equation and you do the same thing to both sides, it remains a true equation. So so performing the same operation, so multiplication or addition to both sides of an equation. Both sides of an equation, preserves the equation. Okay, so let's do an example. We have our system that we want to solve. X minus y is equal to 3, and 2x plus 3y is equal to 1. So what's an example of an operation that we can perform to both sides? Well, if we want to get rid of the, say, 2 in the second equation to solve for y, what we can do is multiply both sides of our first equation by 2. So we by -2 at least. -2 x plus 2y is equal to -6. And now we've got still 2x plus 3y is equal to 1. And so we performed an operation, multiply both sides by -2 to this first equation. And now if we're trying to isolate y, the reason that we wanted this -2 here was because if we add both these equations together, then we're still adding equal things to both sides of one equation. So that should still preserve the equality. And what we'll get is having y isolated. So let's see what happens here. 2x or -2x plus 2x is no x's. 2y plus 3y is 5y. -6 plus 1 is -5. And so we get this new equation that y is equal to, or 5y is equal to -5. And so, that just means if we divide both sides by 5, we get that y is equal to -1. And now we're in this comfortable place where we know if y is -1, then surely we can solve for x using this first equation. So this means that x minus -1 is equal to 3. So x plus 1 is 3, and x must be equal to 2. And so we get values for x and y. Values for x and y that make both of these equations true. I encourage you to pause the video for a second, plug in these values for x and y, and verify that they are, in fact, the equations we get are, in fact, true. Okay, and so the purpose, one of the purposes, at least of this course, is to generalize all of that kind of reasoning to include more equations and more variables. And that'll make it more applicable to harder problems in science and technology or whatever. So let's get some definitions down so we know what we're talking about. So a linear equation in variables x1, x2, x3 up to xn is an equation of the form a1 x1 plus a2 x2 plus all the way up to an xn is equal to b, where we want all of these coefficients, and also b, just to be real numbers. And the reason we use x1, x2, x3 instead of x, y, z is because we rapidly run out of the end of the alphabet there. So we'll use x in a subscript to mean all of our different variables. Great. So for example, if if a1 is root 2 and a2 is equal to -1 and b is equal to 5, we get the linear equation root 2 x1 minus x2 is equal to 5. That's a perfectly good linear equation. We should also talk about what is not allowed. So not allowed. Not allowed is anything of the form like 2x1 squared plus 3x2 is equal to 5. We can't have products of our variables. Fine to have products of our constant terms, but no products of variables. We also can't have x1 minus root 2 of x2 is equal to 1. In here, root 2 is fine. That's just some constant, that's just some real number. The root of our variable, that's what makes it nonlinear. We're just looking at constant times variable, constant times variable. Okay. So then, right, a system of linear equations, or a linear system, is just some collection of linear equations. So for example, we had x and y's before, we could just use x1 and x2 again. So x1 minus x2 is 3, and 2x1 plus 3x2 is equal to 1. It's the same linear system that we had previously. Right, so a solution to this linear system is in this case any pair of values x1, x2 that makes both of these equations true. Any pair of values, ordered pair x1, x2, that makes it makes both equations true, I should say. So for example, we saw a moment ago that at least one of the solutions to our equation is 2, -1. So here we're saying we found that x1 was equal to 2 and x2 was equal to -1. Okay. And we can understand this visually too, because we know that each one of these equations could also be represented as a line in the plane just by solving for x2 in the x1, x2 plane. So this can be visualized. Oops. This can be visualized. By graphing the linear equations as lines. As lines in the, let's say, x1, x2 plane. So we had x1 minus x2 is equal to 3. If we solve for x2, we're going to get what? This is just x1 minus 3. We also had 2x1 plus 3x2 is equal to 1. If we solve for x2 here, we'll get, this is -2/3 x1 plus 1/3. And if we graph both of these, we'll get 2 lines, and you'll see what happens. So let's quickly do a sketch. I use Desmos to do a really accurate sketch. I'll give you the gist of it here, though. And we end up getting 2 lines like this, roughly, where the point where these two get. So here we've got x2 is equal to x1 minus 3. Here we've got x2 is equal to -2/3 x1 plus 1/3. Here's the x1 axis, and the x2 axis. And right, exactly as you'd expect, the point of intersection of these 2 lines is the solution. 2, -1 is the solution to our system. That is the value that makes both those equations true. So this is even showing us that actually this is a solution. It's the only solution. The only time these two lines cross is when x2 is equal to 1 and x1 is equal to 2 and x2 is -1. Okay. This is not the only way that a system can, not the only possibility for a system. The other two possibilities, we could also get a couple of parallel lines, and that would have no solution. There's no points on both of those lines. We could have also had parallel lines. So for example, x1 plus x2 is 0, and maybe 2x1 plus 2x2 is equal to 1. And here, if they're parallel, there are no points in common to both those lines, and you have no solution for your linear system. No common solution, no way to make both of those equations true at the same time. Oop, need a little more space here. Okay, could have also had parallel lines. We could have also had, just like the same equation or the same line doubled up. So maybe if we had x1 plus x2 is equal to 0 and 2x1 plus 2x2 is equal to 0. Here, every solution of the first equation is also a solution to the second. So there are infinitely many solutions. Okay. And so this is a special case of just two equations and two unknowns, but it turns out this captures something more general. And that anytime you've got any linear system in any number of variables and equations, it either has no solution, one solution, or infinitely many solutions. Right. And so we say when a system has at least one solution, we call it consistent. Otherwise, if it has no solutions at all, we say that it's inconsistent. Okay, and we'll talk about matrices in that next video. Take care, everybody.